Okay, our next speaker is Dr. Alexander Goldin. Alexander got his PhD from the Moscow, the Russian Academy of Science. He immigrated to Israel at the beginning of the 90s, like 20 plus years ago. He has very rich industrial background, but at a certain point he decided to actually start his own company called Alango. And he's going to tell us about the other side of a voice, and this is how do we hear and how can we improve hearing for people who suffer from impairment. This is a topic that Alex is very passionate about, as I am. Please, Alex.
Okay, so first of all, thank you very much for giving me this opportunity to present what we are doing. And I will start my talk from the famous quote from Albert Einstein, that no problem can be solved by the same kind of thinking that created it. And in a few moments, we will understand why. So first, I don't think many of you know something about our company, Alango, so I will give just a short introduction. So the company was started in 2002 with headquarters in Israel. We have R&D here, and we have small R&D in Russia. Our business area is DSP, software technologies for different applications for front-end voice and audio and post-processing. Our main business model is IP licensing, and we have rich IP portfolio of integrated low-footprint voice enhancement technology and also some music enhancement. Market penetration, we have about 20 million devices today, mobile phones, cars, conference systems, and others. And our main market today, probably for this year, is automotive hands-free system and automotive communication systems. So this year, or recently, we decided to invest or to try ourselves in a new area, in the area of hard of hearing people. And the question I've made my presentation in a way of questions and answers. So the first question is, what is common between in-car communication system and hearing aid? In each hearing aid and each in-car communication system, we have microphones, we have speakers, and we must do some DSP processing tasks that are, again, very, very similar. So we need to do some beamforming with 2 or more microphones. We need to do some noise reduction, feedback cancellation, because we have feedback from the speakers to the microphones, compression, equalization, and some full band processing like AGC. Today, most communication systems use subband processing and also most advanced hearing aids. So we need to do subband processing, we need to do some kind of analysis and synthesis. And the shared demand is that everything must be very low latency. So the allowed latency is not more than 20 milliseconds, and the optimal is below 10. So what is the main difference between DSP algorithms used in hearing aids and in-car communication systems? Frequency resolution. Most hearing aids use 30 non-uniform bulk scale frequency channels utilizing low delay, low complexity IR filter banks. High quality speech enhancement requires uniform sub-pitch, about 30 Hz frequency resolution, to be able to clean speech from noise between speech harmonics. And 30 Hz resolution corresponds roughly to FET size of 32 milliseconds, or 512 at 16 kHz sampling rate. And direct overlap and add approach with symmetric windows will introduce 32 milliseconds delay, including the buffering. which is too much for hearing aid systems and in-car communication systems. So what can we do to reduce the delay and preserve the frequency resolution? We may use low delay, high resolution filter banks, which is a very interesting idea based on non-symmetric windows. So with non-symmetric windows, we can still preserve good frequency resolution and reduce the delay. Here is the example. So we have this, the green is just the standard hand window, 32 milliseconds length. And we have the blue line, which is low delay analysis window, and the red one is a low delay synthesis window. So we see that the delay here is reduced to 10 milliseconds, which is quite significant. We can also reduce it more. If we look at the frequency resolution of these two windows, that we see that here the frequency resolution is very, very similar. We have a little bit slower decaying shape here, but it's not a problem, we'll see, because we actually, to have this small delay, we also need to move faster to have shorter strolls, and that meaning we don't have any problem with aliasing. So why this approach is not suitable for hearing aids? It's because of the high computational complexity. Low delay filter banks with 30 Hz resolution at 16 kHz sampling frequency require windowed FFT of 512 each 8 milliseconds or less. Performing this FFT with 3 such FFTs each 8 milliseconds, because we need 2 microphones and we need 1 for synthesis, will give us about 10 or 20 megahertz on typical DSPs. And high resolution beamforming, noise reduction, feedback suppression will add 20 or 30 more. So the lowest number that we can get is about 30 megahertz, which is too much for hearing aid DSPs running on small batteries. That generally work at less than 10 megahertz, typically 5. So there is no possibility today to improve sound quality in hearing aids using low delay, high resolution filter banks. So if I were at Intel, I would now say it's time for audio accelerators. But I'm not at Intel, so we need to think of something else. But first of all, do we really need better signal processing for hearing aids? You know, there are several companies occupying the markets. There are many models, advanced digital hearing aids. It seems all fine, but let's look at the facts. So we know that between 40 and 70 people worldwide report hearing loss. The number of hearing impaired people is growing twice as fast as the population. So the question is why? Only 15 or 20% of people with hearing loss use hearing aids. And why hearing aid sales are stagnating for several years? 3 reasons. First of all, hearing aid is considered as a medical device. It's associated with elderly or handicapped people. 15 million people have in the US with hearing loss avoid seeking help. They don't want to use hearing aids. Another reason, high cost due to marketing and distribution. Hearing aid makers spend per device $250 for manufacturing the device, $75 for R&D, $250 on marketing. It is a very strange number, because the device is needed by many people, so it's not something that you buy for pleasure. So retailing, which means audiologists will add another $2,000 to the price, so it's just too expensive. But the third reason is the technology. Technology does not provide the required quality. The satisfaction is not guaranteed. 20 people who bought hearing aid returned them. 7% keep them in the drawer. 70% of those who use them are not satisfied. People prefer old hearing aids over digital ones for listening music. So there is a fundamental problem. What can we do? Like Apple advertising slogan said in '97, we need to think different. Instead of a medical device, we need to think about something different, of consumer electronics device with hearing capabilities. High cost of marketing and distribution. We need to think of distribution via consumer electronics channels. A limited technology. So we need to utilize the best technologies from communication industries. So what are we thinking about? This device is called SALT, Smart Assistive Listening Transducer. This is something that we are developing now. It's a personal hearing enhancer with powerful DSP plus assistive listening device with wide connectivity. So this small device, and I can wear it in a different way. I can wear it here. I can wear it on my hand, like a watch. This small device includes very powerful DSP, 80 MHz DSP, Bluetooth connectivity. Steve Jobs, it's a quote from Steve Jobs, that older people sit down and ask, what is it? And the boy asks, what can I do with it? So what can you do with SALT, besides that it's assistive listening, because it's personal hearing enhancer. This device is a Bluetooth stereo headset. It's two-way intercooled, so if two people can communicate with the distance of up to 30 meters between them using this device, it is a remote microphone. So if two people are in the same, in a crowded, in a noisy place, one which is hard of hearing, he can give this device to another person and get the clean signal, because it will be recorded from much smaller distance. It's a TV listening system that will deliver to your ears the sound of TV. It's a wireless phone leash, so it will report, because it's always connected to the phone, it will report you if your phone is forgotten. It's fall detector with a large emergency button, because you remember it has accelerometer inside. So it's a fall detector. If a person falls and it's motionless, it will detect it automatically. And because it's connected to the phone, it will do the emergency call. You can also do emergency call by just pressing the button. And remember, the probability of fall for hearing impaired people is 3 times higher than for normal people. So these things are very much related. There are other functionalities I will not elaborate now. So the conclusion. So it's time to change the concept of hearing aids to multifunction consumer electronics device with advanced hearing functionality. So we call it personal hearing enhancer. And it's time to do more work on low delay, high resolution algorithms, sharing the same analysis synthesis scheme to be used in personal hearing enhancement. This is a relatively new topic, and we have several things to investigate here. We need to do some optimization on Windows, LS versus resolution. Advanced beamforming technologies for different microphone configurations. This device, this SALT is just the first in a line. There will be different devices with different configurations, all requiring signal-to-noise enhancement. Transient noise reduction, very, very annoying for people, you know, all kind of clicks, knocks, and pop sounds, because they are amplified by the device. Feedback cancellation technologies and loudspeaker response correction. That's what we are doing at Alango and also at hearing.com. That's, thank you very much. End of my opinion.
Thank you very much. Questions?
Very interesting. You have a lot more DSP power in this device than typically used in hearing aids. One of the things that most hearing impaired people suffer from is when they have babble noise rather than just background noise, stationary noise. Are you thinking of putting in processing, DSP processing, to handle that problem?
Yes, of course. That's why we need more power. We need to run more advanced algorithms. And we have this, because of this additional power, we have this luxury of performing more than it's available in a typical hearing aid. Typical hearing aid, you actually have 5-10 megahertz, and you are very, very limited. Even if you have audio accelerators like A50 inside, still you cannot do much to cope with types of noises, to classify different types of noises. So this is our vision, that with more power we will be able to bring something much better, much more sophisticated.
How many microphones you have?
In this device we have 2 microphones, 2 digital microphones, low noise microphones.
He knows to do with 2 microphones what you can do with 8. I guarantee you. Okay, question. Yes, please.
If you can provide some kind of SDK or an API for a device, which will allow me to develop a new algorithm which use your device for different...
Yes, it's also, thank you for this question. Yes, we are planning doing that. It's a platform. It's a platform that will be open for, first it will be open for applications on the mobile phone. So you will be able actually to program this device for different applications, because again, it's a platform with accelerometer, with vibration motor, with a microphone, etc. You will be able to utilize this platform for different applications, which may not even be in the area of hearing.
Yes, please.
Do you think of taking advantage of the additional microphones in the cell phones? Because you said you have communications.
The question was whether he would leverage the additional microphones in the mobile phone itself.
We're not planning doing that. We haven't been thinking about that, about the potential advantage of doing that. So maybe we'll use your...
Alex.
Yes.
Hi there, my name is also Alex. And yes, what you presented is a very, very good idea. And actually Qualcomm are working on something very similar. So we get to the same analysis as you. And yes, you can you can use the phone also to do the analysis. And actually we also have a platform that is already working, also almost on the market. And yes, this is very, very nice. And it's good that other companies are working also on these ideas.
Okay, so great companies think alike.
Exactly.
Okay, thank you very much, Alex.